Hello and welcome to episode 2 of this series on Coxeter groups. Today we'll be covering the Bruhat order and of course some properties and examples that go with it. Right, well, let's get started. First of all, let's quickly discuss what a partial ordering is. Okay, so for a partial ordering, you take some set, maybe like X, right? Okay, and a partial ordering is some relation, okay, like that's got, which will give this symbol, okay, such that for all A, B, and C in X, we have reflexivity. Okay, so that says that A is less than or equal to A. Okay. We have antisymmetry. Okay, and that is where if A is less than or equal to B and B is less than or equal to A, then that implies that A must equal B. Okay, and finally we've got transitivity. Okay, so that says if A is less than or equal to B, B is less than or equal to C, then that implies A less than or equal to C. Now, I've been saying less than or equal to for this relation, that is kind of abstract, but the reason I say less than or equal to is because it is basically less than or equal to. It's a way of having an ordering, a way of comparing elements in your set X. Okay, and this is a partial ordering. We can make it a strong ordering if we just remove the or equal to condition, and then you'd have to change the anti-symmetry law as well a little bit. Okay, but don't worry too much about that. There are some important words regarding partial orderings that we should be familiar with. Okay, and they include an interval. Okay, and so that is if you've got A and B. Okay, so then this just equals the set of X in X such that X is anywhere between A and B. Okay, we also have covers. Okay, so and we denote that by a triangle like this, and that says, so if you have A is covered by B or B covers A, then that means that the interval A to B is precisely A and B. Okay, so there's nothing in between them. So a good example I would say is in the integers, 2 covers 1. Okay, there are no whole numbers between 1 and 2, so 2 covers 1, or 1 is covered by 2. Okay, we also have chirality. Okay, and that will play an important part later on in this series. But what that means is it basically depends what side you're multiplying or adding or whatever on. Okay, so if you've got X, Y, and Z in your set X, okay, and you have X less than or equal to Y, then X times Z is less than or equal to Y times Z, right? Then then this relation here is right chiral. Okay, so basically you're multiplying by z on the right. Okay, so this relation is right chiral. And there's an equivalent version for multiplication on the left for left chiral. Okay, we also have isomorphisms. Okay, and an isomorphism of a partial ordering says that if you have, let's actually use, if you've got A less than or equal to B in the red partial ordering, okay, and okay, and you also have A less than or equal to B. Oh, hold on. B, yep. Okay, in the green partial ordering, I'm not sure how clear that is on the screen, but you know, you can hear what I'm saying. Then the red and the green are isomorphic. Okay, and this has to be true, of course. This would have to be true. This would have to be true for all A and B in X. Okay, so let's put for all A, B in X. Okay, and then finally, we have automorphisms. Okay, and these are functions phi. Okay, or you know, whatever you want to go with. Okay, so phi goes from X to X. Okay, and phi is an automorphism of a partial ordering if for all X and Y in X, if X is less than or equal to Y, then phi of X is less than or equal to phi of Y. So basically, it doesn't change the order, basically. Okay, and there is also anti-automorphisms where this basically swaps the partial ordering around. It reverses everything. So if you've got X less than or equal to Y, then you end up with phi of Y is less than or equal to phi of X. Okay. Now that we've got that out of the way, let's talk about the Bruhat order. Okay. Well, okay. Well, actually, before we do, let's consider trying to create a partial order by the length function that we defined in episode 1. Okay, where I wonder if I've still got that here somewhere. Yep. Okay, so it's the fewest generators, okay, this length function L, okay, required to write W. Now, that does work as a partial ordering, okay, but the problem is that if you use that, it's rather coarse, okay, there is, you know, a lot of things related here and there, and it gets, you know, you don't really get anything meaningful out of it, okay, so we've got to think of another way of ordering our group, our Coxeter group W. And the first thing that we might think of is ordering by generators. Okay, that is, an element is considered less than if it can be reached by multiplication by a generator. Okay, so what exactly does this look like? Well, if you have a Coxeter group, WS, okay, and T equals set of reflections, and remember that that is equivalent to conjugations. Okay, then let W and W prime be elements of W. Okay, then W is less than or equal to W prime in the Bruhat sense. So to denote the Bruhat order, I'm going to be writing less than or equal to with a subscript B next to it. Okay, if there is a chain with W equals W naught, W1 up to WR minus 1, WR, and that equals W prime, where WI arrow WI plus 1 means there is some T in T, okay, little t in big T, such that Wi times T equals Wi plus 1. And we also have the length of W is less than or equal to the length of W prime. Okay, that's very important. And this is the Bruhat order. It's named by Verma after a mathematician, Francois Bruhat, because of the relation of this ordering to the Bruhat decomposition of Weyl groups. And you can read up about that in your own time. But it's beyond what we're going to be talking about. Okay. And you can check for yourself that this is a partial ordering against the definition I just gave. Okay. But let's have a look at some properties that we can spot straight away. So first thing that we notice is that if we've got W1 less than or equal in the Bruhat sense to W2, then this implies that the length of W1 is less than or equal to the length of W2. Okay, yeah, I mean that's one of the things in the definition. Okay, we also have that if W1 is less than or equal to W2 in the Bruhat sense, okay, then this is true if and only if the length of W2 times T, sorry, and this is true if and only if the length of W1 is less than the length of W2 times T. Okay, and I believe it does have to be a strictly less than symbol here. Okay, because you could have some reflections where they don't, the length isn't affected, but yeah, you get some things happen. If this isn't quite right, I will put an edit in the video now. Okay, you'll have something will flash up saying, "No, Goran, you are wrong." Okay, and then the third observation we have is that the identity is less than or equal in the Bruhat sense to all, or all W in W. Okay, basically the identity element is less than or equal to every element in W. Okay, in our Coxeter group. In fact, we give the identity E length 0 by definition. Okay. However, the thing is that, if you want to find the Bruhat order, having to find this chain every time, okay, is a bit long, right? Okay. It's a bit long, right? It's a lot of work. Okay, it would be nice if there was a sort of a quick method that you could use. Fortunately, there is. It's called the subword property. Okay. Okay, the subword property. And that says that, so you have W in W, okay, and W can be represented in this way, S1 up to SR, as a reduced word. Okay, so this is the minimal decomposition for W. Okay, then W prime is less than or equal in the Bruhat sense to W if and only if W prime can be obtained as a subword of W. So basically, if there is some if W prime equals SA up to SB, where A and B are between 1 and R, okay, then, and that is, yeah, okay, then W prime is less than or equal to W, okay. And this is a lovely property. It it reduces the amount of work needed to calculate the Bruhat order. Okay, and you can look up the proof in my project, which is in the description below. Okay, but I'd like to talk about a couple of corollaries of that theorem. Okay, the first is that if you have I, a subset of S, then the Bruhat ordering, of the group Wi respects that of W. So basically, if you take a subgroup of W, okay, then everything retains its partial ordering under this Bruhat order. Okay, and we also have if W1 is less than or equal to W2 in the Bruhat sense, then there is a chain W1 equals to X1 less than or equal to X2 in the Bruhat sense, less than or equal to up to xk, and that equals w2. So this basically says that if you take that chain that we used in the definition, okay, then you could stop things sort of at intermediate steps, and you would get this chain, okay. And finally, the third corollary that I want to point out is that the Bruhat order is achiral. Okay, and what does that mean? Okay, well, it means that it doesn't matter which side you multiply on. The Bruhat order doesn't get affected, basically. Okay, which I think is pretty interesting that you've got this this system, and this partial ordering, and often in groups you don't have like commutativity. It really does matter which order you do the multiplication in, but for the Bruhat order, doesn't matter. Okay, so that's nice. Okay. We also another interesting fact about the Bruhat order is that if W1 is less than or equal to W2 in the Bruhat order, then this is true if and only if W1 inverse is less than or equal to W2 inverse in the Bruhat order. Okay, now the reason I'm mentioning this is that this kind of goes against what we're used to with partial orderings, okay? Because if we take less than or equal to in the real numbers, in the sense that we're sort of used to, okay, then we would see that if you've got, like, say 2 is less than or equal to 10, yeah, okay, and you take the inverses, then that reverses the partial ordering. You end up with 1 over 10 is less than or equal to 1 over 2. Okay, whereas here in the Bruhat order, okay, you take the inverses and the partial ordering doesn't change. Okay, I mean that's weird in its own right, and the reason is that to get the inverses of elements in a Coxeter group, you just change, you just reverse the minimal decomposition. So if it's S1 up to SR, then the inverse is SR down to S1. Okay, and if you've got a subword, contained over here, then you'll have the same subword can be found, or similar one can be found on the other side. Okay, there's a little bit more to the proof, I think, but you could, again, you can look that up yourself. Okay, so when I was talking about interesting and important words associated with partial orderings, I mentioned something called automorphisms. Okay, and the reason is that well, this this proposition, this idea of things being less than, not things being, the idea of the inverse not affecting the partial ordering, gives rise to the following automorphisms. So we have that the map W to W inverse is an automorphism of the Bruhat order. Okay, and that's just formalizing what I just said. Okay. Okay, so we also have the we should also consider the descent sets, sorry. Okay, And so if W1 is less than or equal in the Bruhat sense to W2, and S is in the left descent set for W2, but not the left descent set for W1, then W1 is less than or equal to SW2 in the Bruhat sense, and SW1 is less than or equal to W2. Okay, now this all looks a little bit confusing, but what it is something called the lifting property. Okay, and and it's a bit easier to see in a diagram. So if you've got hold on. So here you've got so this is SW1, this is W1 here, and you've also got SW2 and W2. Okay, then basically you've got this sort of system. You can you can multiply if you've got this set up with the descent sets, then it basically lifts up W1 or W2 in whatever manner you're needing it. Okay, which it's pretty interesting. Okay, corollaries of that is that if you've got S in S, okay, T in T, and W in W, with S not equal to T, okay, then you can have W covered by SW and TW, and that implies that SW and TW is covered by STW. And we also have, if you've got S1 and S2 in S and W in W, then W covered by S1W and W S2 implies S1W and WS2 are covered by S1WS2, which is or W equals S1WS2. Okay, and again, these are a lot easier to see in a diagram. So if you've got W here, TW, SW, STW, so this is the first of the two corollaries, you end up with this sort of image. And for the second one, you got W down here, WS2, S1W, and S1WS2, and that looks something like this. Okay. Now that we've defined all of those and, you know, had a look at those examples, okay, let's look at an example, okay, and we'll look at D6 because that's one of our preferred examples to be looking at in this series. Okay, so we've got D6 and we're using the generating set S bar. Okay, and let's think about an interval in this. So if we've got S1 and S1, S2, S1, S2, okay, and again intervals, but for the Bruhat order we put a little subscript B in, okay, and what does this interval look like? It looks like S1, S1, S2, S2, S1, S1, S2, S1, S2, S1, S2, and S1, S2, S1, S2. Okay, basically all the subwords that contain S1, basically. Okay, and we can also look at coverings. S1 is covered by S1, S2, and S1 is also covered by S2, S1, because, you know, you can multiply by S2 on the right hand side here and you get S1, and S2 on the left hand side here to get S1 as well. Okay, that, you know, that's what covering is. I'm also just going to put up the Bruhat graph, okay, of D6, and what you can see here is all of the relations, all the elements that are related to each other in the Bruhat sense. So, you know, it's quite busy, you know, admittedly, okay, but yeah, it's a bit nice to sort of see, you know, where the connections are. Okay, now I would like to move on, and I'd like to move slightly away from complete abstractness, okay, and consider the Bruhat order specifically on finite Coxeter groups, okay. And it turns out that that if you have a finite Coxeter group, then you will have some maximal element, okay, W0 I will call it, okay, and this is something where W is less than or equal in the Bruhat sense to W0 for all W in W. Okay, so that's what a maximal element is. Okay, the corollary of this is that if you've got some element X in W, okay, and the descent set of X is all of S, okay, so it's all the generators that shorten the length of X, then X is maximal, okay, X is precisely the maximal element, okay, you know, it's pretty interesting, okay. Okay, we've also got a few properties. So first one, W0 squared is the identity. Okay. The length of W times W0 is equal to the length of W0 times W, and this is equal to the length of W0 minus the length of W. Okay, so, you know, you can sort of picture why, this is true, you know, W0 is this maximal element, so it's got the longest length. And if you multiply it by anything else, you know, you're going to shorten it by whatever that element's length is. Okay, we also have the length of W0 times W times W0. So basically you're conjugating by W0, and that brings you back to the length of W. Okay, so conjugation doesn't affect the length as long as it's by W0. Okay, you know, and you can prove that one basically by applying this one twice. The left associated reflections of W0 are all of the reflections in W in your Coxeter group, and the left associated reflections of W0, W times W0 is all the reflections without the associated ones for W. Okay, and the length of W0 is also the size of all of the set of reflections. So if you take the number of reflections in your Coxeter group, that is the length of the maximal element. Okay, and you know, you can prove all of these in your own time, or have a look at my paper that I wrote, link in the description below. Okay, but let's have a look at some other automorphisms of the Bruhat order on finite Coxeter groups, because we saw earlier that the inverse map doesn't affect the Bruhat order, you know, and question is, are there any others? Okay, yes, there are, but with some caveats. Okay, so first of all, assuming that W is finite, okay, then if we multiply by the maximal element, so multiplication by W0, so the function that takes W to W times W0, and also W to W0 times W, so left or right multiplication, these are anti-automorphisms. Okay, so you know, these reverse the order, and the proof of that relies on basically finding these chains and then, you know, working out what goes on with that. You know, you can read that up yourself. But if you apply the W0 this map twice, okay, so W sent to W0 W W0, so conjugation, okay, is a normal automorphism. Of the Bruhat order. Okay, so these are automorphisms of the Bruhat order. Okay, so that's two more automorphisms that we've got. Okay, so, well, not more, just two. Sorry, that's two anti-automorphisms and then two normal automorphisms. Okay, so we've got the inverse map and maximal element conjugation. Those are our automorphisms. What else is there? Well, for Coxeter systems of rank 2, okay, and I can't remember if I mentioned rank in the previous video, so quick reminder if I did, and here it is if I didn't. Rank just means the number of elements in your generating set. Okay, so rank 2 is basically dihedral groups. Okay, yeah, which so is Dn. Okay, then there are 2 to the n minus 1 automorphisms okay, and the group of automorphisms of the Bruhat order, so aut BR of W, is actually isomorphic to Z mod 2Z to the power of n minus 1. Okay, so the way this works is that you've got one automorphism for every element, basically. Okay, which, I think, that's pretty cool. However, for Coxeter groups of rank 3 and above, so rank 3 plus, okay, it's a little bit, the automorphisms are a lot less exotic. And it can be proved that for ranks 3 and above, okay, there are only two automorphisms of the Bruhat order. HAT. Okay, and they are what we just looked at. They are the identity map and the inverse map. Okay. Okay, and the proof can be found in my project link below. Okay, and I don't think I go into the total detail. Okay, for that there is a link to the paper that does prove it in full detail in the bibliography of my project, which you can look that up. Okay, so that's the Bruhat order. Okay, or for finite groups. Okay, in general, I'd like to turn our attention now to SN. Okay, the permutation group. Okay, firstly, coverings in the Bruhat order are quite nice. Okay, if you've got, in fact, I'll use a new sheet. Okay, if you have got X and Y in SN, okay, then Y, hold on, Y covers X, or X is covered by Y, if and only if Y equals X multiplied by some transposition AB. Okay, for A less than B, this is in normal less than sense. Okay, and X of A is less than X of B. So what is, oh, and there is no C with A less than C less than B, and X of A less than X of C less than X of B. Okay. The proof of this uses something called inversion numbers. Okay, so that's the functions that sort of flip flip the elements A and B, or the numbers A and B. Okay, so what does this mean? So if you can find a transposition, okay, with this, okay, and you also have that A and B are sort of not necessarily consecutive, I don't think, but the permutation X doesn't make X of C between X of A and X of B, then you've got a covering there. Okay. But what about finding the Bruhat order of elements in Sn? Okay, because Sn grows factorially. You know, the size of Sn is n factorial. Okay, and you know, once you get past sort of 4 or 5, then this factorial, you know, this is massive. These numbers, okay, you know, and I don't know about you, but I would not want to be finding Bruhat chains, you know, with you know, in sets this large. Fortunately, there is something called the Northwest criterion, okay, and that we can use to determine the Bruhat order, okay, and that says that, well, first of all, what is the Northwest criterion? So let's Northwest criterion, okay, and that says that you take x of ij, okay, and this thing is equal to the size of the following set: the number of elements a in between 1 and I, such that x of a is greater than j. Okay, and practically we use it in the following way: you draw a graph, okay, labeling the axes with a and x of a, and then you plot axa, okay, and x of ij counts the number of points northwest, so up to the left, of ij. Okay, so ij being this the coordinates. Okay, and you know, so this, okay, is the Northwest criterion, and we have the two things are equivalent. So first of all, x of x less than or equal to y in the Bruhat sense, and x of ij less than or equal to y of ij for all I and j in 1 to n. Okay, so what's this saying? Basically, this sort of shortcuts the Bruhat chains that are needed. Okay, the full proof isn't in my project. I only do the first one going from the Bruhat order to the Northwest criterion. Okay, but you know, it's all well and good, but we should really try and see this in action, I would say. Okay, so if we take let's take w equal to 2, 4, 3, 5, 1, and w prime equal to 1, 2, 3, 4, 5. Okay, upon first examination, you know, it is unclear whether w and w prime are even comparable in the Bruhat sense. Okay, and if we use the Northwest criterion, okay, which I will put up on the screen now, because I don't really want to have to draw this graph myself right now, okay, then we see that for I and j between 1 and 5, okay, we get that w prime of I and j is less than or equal to w of I and j for all I and j, and therefore w prime is less than or equal in the Bruhat sense to w. Okay. So yeah, in summary, the Bruhat order can be characterized by multiplication by an element w, you know, an element in w, and seeing how that affects the length. Okay, but then here's a question: What if you restrict it to generators? Okay, well, make sure you catch episode 3 to find out. But that's the end of episode 2. I hope you enjoyed it. If you did, hit like, hit subscribe, do all the stuff, and I'll catch you in the next one.